Wireless News. My name is Sean Kinney, and I'd like to welcome you to our webinar today titled, What New Indoor Opportunities Will 5G NR mmWave Bring? I'd like to thank you again for joining the discussion, and by way of housekeeping, this webinar will be recorded and the video will be made available on the RCR Wireless News YouTube channel. Slides will also be made available to registrants. And we've reserved some time toward the end of our session for Q&A, so please use the webinar portal to submit questions throughout the presentation. Now, to set the scene, the use of mmWave frequencies for commercial cellular deployments has rapidly accelerated in the past 2 years. We went from broad skepticism about mmWave's ability to support mobility to, in the US, commercial deployments from both Verizon and AT&T using high-band spectrum. On the device side, Qualcomm's led the charge developing SoC support for mmWave as well as the necessary RF front-end and antenna modules. Those efforts have come to fruition with commercially available handsets, mobile hotspots, and consumer premise equipment. Right now, the current focus for mmWave 5G is on outdoor deployments, creating gigabit coverage in urban cores and key business districts and venues, but the paradigm that applied to LTE is still in place. The majority of data traffic originates indoors. So today we're going to explore the indoor opportunities 5G NR at mmWave frequencies can enable. To take us through that, I'd like to welcome Alex Hulkman, Senior Vice President of Corporate Engineering at Qualcomm Technologies. Alex leads end-to-end engineering services with more than 1,000 engineers and external partners. Alex has been with Qualcomm for more than 2 decades and he holds more than 30 patents. Now I'd like to turn it over to Alex for the presentation.
Yeah, thank you, Sean, and welcome everybody to this Qualcomm RCR wireless webinar. And I'm here today to discuss how mmWave is progressing. We have a lot of interesting opportunities ahead, and I want to show you what we've been up to, what my team has been looking to do with mmWave, some of the new ways that we can use it. Thanks for the background. You know, like Sean said, my team has been working with mobile network operators for the last year or year and a half, and equipment manufacturers and OEMs and industrial companies to figure out how to best deploy mmWave. And as you know, 5G, the way it's been designed is not just for enhanced mobile broadband. 5G can really be placed anywhere. It's been done with, it's 4G with a gazillion amount of flexibility into where you can actually place it. So to that end, a lot of effort was done on the 5G specifications to work on the higher bands, which is mmWave. And if we actually look at where the specifications are, this, of course, started in Release 15. Release 15 does have the support of both mmWave and Sub-6. But, of course, there's additional things that are going on in Release 16 and even Release 17 type items. But today, we'll just focus on what's the near term and what kind of things are going on in Release 15. If you look at our dot here, is we are here, and this is where at least the first commercial deployments that we're going to see worldwide, they're all going to be based on Release 15. And of course, the whole ecosystem around the Release 15 spec in terms of smartphones, connected laptops, CPE. So we're just getting started. There's actually quite a bit of excitement even ahead that we haven't done yet. So let me go through, give you a perspective on where mmWave is around the world. In North America, we already have 2 operators that have launched mmWave. In Japan and Korea as well, mmWave is either in commercial deployment or about to get into commercial deployment. In Europe, looking at both Europe and Russia, there is millimeter wave specifically in Russia, and the European area we're getting involved in some trials, and I think it's looking like it will happen sooner or later in that region. China specifically, very interesting, as we will see the amount of capacity and the amount of things that you can do with millimeter wave. We would be expecting China very soon to adopt millimeter wave because of just the sheer amount of capacity that they need in some of the cities. So I think it's inevitable. So let's talk about where we are today. And 5G, as you know, has a tremendous amount of complexity, but the good thing that we're seeing in the market is when we compare to 4G, when 4G launched, it's a very gradual launch. Only a few operators around the world started launching, and then, maybe 6 months or a year later, additional operators would launch, and very few OEMs. With 5G, it seems the whole ecosystem, the whole industry have actually jumped on this. So to this date, we have more than 20 operators around the world that have actually decided to launch 5G. And along that, you have the operators, you need devices. So we have about 20 OEMs and more coming up every day that have announced products for 5G. So very, very strong momentum with 5G. And I will now talk specifically about millimeter wave. So what is millimeter wave? If you look at the spectrum, 5G initially, it will be in 2 bands. One we call sub-6, which is below the 6 gigahertz. And the upper band, where 5G will be used for now, is in the higher band, which is from 24 gigahertz all the way to 100 gigahertz. And we call that millimeter wave. Now, of course, 5G can work in many other bands, but at least these ones are the ones that initially were looked at. And specifically in millimeter wave, why was that picked? Well, the amount of spectrum that is there is really what, as we were looking at 5G, is what was needed for the amount of bandwidth and the amount of data carrying capacity that we wanted to have. So there's a large amount of spectrum there when you compare to the lower bands. But of course, that spectrum comes with its own challenges. And we will talk about that and how we overcome those challenges. But the bottom line is millimeter wave, huge amount of spectrum. And when you have a large amount of spectrum, you can actually generate very, very fast rates, a lot more capacity. And with 5G, you can have lower latency. So to that effect, as you know, 5G, you can get fiber-like data speeds. You're talking multi-gigabits-per-second. And once you have that kind of connectivity everywhere, then of course, all kinds of things are possible. Let me go specifically about where millimeter wave its use and specifically what bands. Right now, I'm not going to go through every one of the different countries, but you can pretty much see 26, 28, and 39 gigahertz are the most common bands that are being used around the world. Right now, as I'm aware today, the devices that are launching are supporting both 28 and 39. And very soon, as the 26 gigahertz band starts getting announced and deployed, they will actually, the OEMs will start coming up with that band support as well. So today, only 2 bands, but now as operators come in, OEMs will start including some of the support for the additional bands. So millimeter wave is challenging, and there's a lot of skepticism even today about millimeter wave. You know, does it work? Does it not work? What kind of things that we can use them for? And people were saying, well, millimeter wave doesn't really propagate much. There's a significant path loss, very limited coverage, and it's true. That is correct. However, there are a lot of techniques that you can do to overcome millimeter wave, some of the challenges, and I will go through some of those in terms of how you can reuse the different beams and different configurations that you can do to actually overcome some of the challenge on coverage, which sometimes could work to your benefit. One thing out of this webinar maybe if there's one thing that people can take out of this webinar is that millimeter wave is really a capacity solution, not a coverage solution. So, and I'm sure you can envision a lot of places where you need lots of capacity. And this is where millimeter wave comes to the rescue. So if you're looking for coverage, there's a whole bunch of other ways that you can get it. But the key is that millimeter wave will offload and will provide that capacity that is needed. The other issue that people have talked about is, well, you need to have line of sight. And yeah, traditionally, millimeter wave has been used for point-to-point links, satellite links, point-to-point links, line of sight links. However, with beamforming, beam tracking, reflections, there is multiple antennas. There's a lot of things that you can do to overcome. For example, if your hand blocks one of the antennas or one of the beams, then there will probably likely be another beam or another reflection that gets picked up, or another antenna on your device will pick that up. So devices may have 2, 3, 4, maybe more antennas located in different places around the device so that at any one time, you're not blocking the millimeter wave signal. So if you're, for example, playing a game and you shift the device and your hand is blocking, then there will be, the idea is that you always have an antenna that is available to receive and send the signal. The other item that people talked about is, well, this is proven millimeter wave for point-to-point links, wireless backhaul satellites. But similarly to the previous note, once you actually have this beam tracking and beam forming, then you can actually do a lot of handovers, things that we have done in cellular systems for a long time. So we know how to actually switch beams, how do you actually go through that kind of challenging signal when it comes in and it disappears, and how do you actually hand off across the different beams. And finally, they said, well, millimeter wave, it takes a lot of power to get this done. There's thermal challenges to put that inside a smartphone. But the technology is such now that Qualcomm has come up with quite a bit of innovation around millimeter wave modules and how you actually put millimeter wave in a handset. So we have very small antenna modules, very power efficient, and you can actually have multiple of these modules on a device. And we've actually shown it. There's smartphone form factors, and actually there's devices coming out with this technology any day now. So from a technology point of view, like I said, we started working on this maybe a year and a half ago. Of course, at first, there will be, not all the bandwidth we expected, but we showed about 1 gigabit. Soon after we started getting the full bandwidth, I think we were starting to get 800 megahertz, and we were getting just under, about 4.5 gigabits per second. And that was on trials that were not using a form factor device. And then we said, okay, what would happen after we actually put it on a form factor device that you can hold in your hand? And we showed that almost a year ago, where we started doing over-the-air calls. And then finally, our reference design that we announced not long ago, and now, of course, more than 30 commercial devices that we'll be launching with mmWave. So let's talk about some of the opportunities, some of the things where you can actually use mmWave. This webinar talks more about indoor, but certainly for outdoor, there is a good case as well. And I will discuss that both outdoor and indoors. For outdoors, we did a study. People will come and ask us, if I had to deploy mmWave, how many sites will I actually need? Am I going to have to, quadruplicate the number of sites that I have, or times 10, or how do I do that? So the first study that we did is we said, well, let's assume that you don't deploy any more sites, and you actually put in a mmWave site on every site that you currently have. And this was the study that we did across multiple operators in multiple countries. And you can see that the percentage of coverage was much better than what we would have expected. In many cases, assuming a reuse of an existing site with LTE, we were getting maybe 75%, 60%, 75% without adding any additional sites. Of course, we took some of the areas that were dense, but these are fairly significant clusters. And the reason that it works out like this is because some of these sites were meant for capacity anyways. So, which is exactly where mmWave comes in. So even today, without adding any additional sites, an operator can get a significant amount of offload from their 4G network into 5G. This one is a use case I'm pretty excited about, and it has to do with fixed wireless access. And one of the things that have excited some of the wireless operators is that, well, now I can reach what they call the last mile. I can reach, I can do fiber-like speeds without needing to put fiber to the home. However, there is some challenges around that because, like I said, you could have blockages. mmWave does not penetrate from the outside to the inside. So you have to find ways to somehow capture the signal outside and then bring it inside. In case of a urban deployment, you could have receptors up on the rooftops. In the case of suburban deployments, you can have the antennas up on roofs. And from an economic perspective, if you actually look, let me go to this slide. From an economics perspective, if you actually look at a very dense city like this, it is very economical. It's very, there is a good ROI in actually being able to cover a large amount of buildings with potentially existing sites that an operator may have on some of these rooftops. Today, there are many companies that do point-to-point links across buildings to to, where it may be too expensive to run fiber to every building. So what they do is they go over the air on the rooftops. But if you can leverage one network instead of having multiple networks, if you can leverage one network that provides both, reuses in existing sites and is able to cover a large amount of buildings, then what you do is you actually put the CPEs up on the rooftop, and then you distribute via wireline inside the homes, which is what typically many companies are doing this today as a fiber extension. And we did some analysis on that using existing operators' towers. You can get coverage of like 80% of the buildings with a pretty healthy downlink and uplink speeds. And if you have an average usage of a building with multiple stories and multiple families per story, you could provide broadband service of 400 megabits per second to a home in many countries, Asia, Latin America, many countries I can think of where this would be a very good broadband speed to actually even today in some of the developed countries too. But it's a very cost-effective way to get broadbands into dense cities. So this is the specific study that we did, the cluster that we took, the example to get this kind of rooftop reception with a CPE, and then the wiring is distributed internally like it's currently being done for other broadband services. Let me go to another use case. How do we know what is the link budget and what is going to be the coverage prediction that we talked about? So we built a tool where we actually take, we actually develop the link budget based on propagation losses and transmit and receive power, and we actually feed that into a planning tool. In there, we actually bring in the terrain data and the site, and with all that data, we come up with the coverage prediction. But of course, we don't just believe directly the coverage prediction. What we do is then we go and take actual measurements around that prediction so we can verify if our prediction was accurate or not. And we will do spot checks. And that's how we validate what the predictions are. So this is an example of a link budget. I believe this one is for a stadium-like scenario. And you can see the different numbers around downlink and uplink and what the different data rates, what the target data rates were based on certain assumptions of spectral efficiency that you can get. In terms of, now of course, this is the cell edge. Some of the speeds here are cell edge data rates, which is a very healthy, if assuming you have 800 megahertz, it's a very healthy 320 megabits per second. That is your edge of cell. As you get closer to the cell, of course, you're talking in the gigabit range. So let's discuss the examples. This is kind of the propagation plots that I was talking about, and each dot, each color represents a measurement that we've taken to verify if our predictions were accurate or not. And you can see the color, some of them matched the color of the prediction, some of them didn't, so we adjusted the predictions. But in general, it looked fairly accurate. So let's take some of these examples on where you would deploy mmWave. Of course, we want to cover not just rooftops. We want to cover enterprises. We want to cover airports. We want to cover transportation hubs. Anywhere where there's large amounts of people, stadiums in particular, dense deployments, whether that is a stadium, a concert, all these where current technologies are not able to keep up with the customer demand. When people are uploading pictures, where people are sharing experiences, when people need to know some information, when you have a lot of capacity, some of these networks basically do not hold up. So you need the capacity, and mmWave provides that relief. So let's take an example for venue deployments, and for this particular one, we chose the 28 gigahertz band, and we took one concert venue. This concert venue brings in, I think, close to 100,000 people, and we assumed, okay, what if, and this venue is currently being served by LTE, and for the demand that they had today, they would have had to do it with about 38 sectors of LTE. If they did it with 5G mmWave, you would only need about 16 sectors of 5G mmWave, so you need a lot less sites. Not only that, but the user experience, the increasing capacity, you can increase it by 10 times what you would have had with LTE, and the user experience close to 100 times the throughput. So not only you use fewer sites, but your end user experience is orders of magnitude improved. And we tested that, of course, not just on a music festival. I'm going to give some examples where we've actually done one-to-one comparisons of LTE deployments or Wi-Fi deployments versus mmWave deployments. So this one, we took a convention center, and we actually looked at where the current G-Node-B antennas were deployed with LTE on a DAS. This one specifically, if you recognize the names, this is the Las Vegas Convention Center, where CES is done every year. So we said, okay, what if we wanted to have a 5G consumer electronics show? What would it take? How many sites would we need? So we went ahead and took a couple of the key halls, and we made some assumptions. And actually, we actually had the maps on what the walls were made of, the booths, and we received the locations of where all the sites for LTE were. So we went ahead and we placed mmWave antennas on exactly the same places that you would have LTE antennas. And we only had a few issues around that center office area where you see some of the red. There are some internal walls, but overall, we had 95% coverage and 95% uplink coverage using the same spots where they had antennas today. But of course, the user experience was tremendous. You had a median burst rate of 5 gigabits per second. So that's the kind of capacity we're talking about when you actually put mmWave indoors. And then we said, okay, what if we actually, the previous one was we put it where the LTE antennas were. On this one, we said, okay, what if there was a convention center that had Wi-Fi access points? We're trying to figure out how you make this deployment easy, right? So where you have Wi-Fi access point, you already have power, you probably already have access to backhaul. So that's the idea, is how do you deploy this in a simplified way so it doesn't require that much work. So if we actually put millimeter wave in the same spots where the existing Wi-Fi access points were mounted, we had a very similar experience where you would have, you did not get 100% coverage, but we had about 87% of coverage, and uplink coverage was a little bit better at 92%. But again, the experience compared to what the existing Wi-Fi was is an order of magnitude, and just because the amount of bandwidth that you have with millimeter wave and the downlink median burst rate was 3 gigabits per second, which means, basically a lot better performance that you can get with Wi-Fi. So then we took it to an indoor stadium. It's a similar results. We actually put just one site. We put it about 6 meters above the ground in front of all the seating area. This would be, auditoriums, or even, concert halls, and very, very good coverage throughout, just because of, all the reflections that we have there. So we had 100% coverage, which is a properly placed site. It may not always be possible to put that site, exactly where you want it. So, worst case, you will have to put, 2 or 3, but we're not talking large amounts of sites to absorb the capacity for the kind of experience. And we're talking about many players in the industry, especially the entertainment industry, is being able to figure out different experiences. What can you do when the devices can actually experience multi-gigabits per second? So what kind of new experiences can you offer to your audience? So very creative, some of the artists that we are talking about things that they want to do in terms of fan interaction once you have these kind of speeds. The next area is not only we want millimeter wave on our phones, but we also want it on our laptops. We would like our laptops to be lighter. We want our laptops to weigh less. We may want all our data to be secure on the cloud, so that in case we lose our laptop, everything is secure on the cloud, and we just have extremely good connectivity, so we always have data when we want it. So in order to do something like this, you need enterprises to have good coverage and good connectivity. So we went ahead and said, okay, let's take our own Qualcomm building. This is a floor plan of one of our floors here in headquarters. And we picked this floor plan because it had, larger rooms, smaller rooms, glass, conference rooms. It's a mix of different types of areas. And we said, okay, what if a Qualcomm employee, as a typical enterprise, would put millimeter wave on their laptop? What kind of coverage that person would have as he goes across to, his office or the conference rooms and the different areas in the building. So the first place we started is we went to our IT department and we said, okay, where are all the Wi-Fi access points in that building today? So we got a map of that. You see the pictures of where our access points are. And then we went ahead and put that in our modeling tool. We said, okay, what would it be if we had 5G millimeter wave on these same spots? So we went ahead and did that, and we had pretty much good coverage throughout. Again, same story. The speeds that you would get, it would be something that would be very acceptable to have a good laptop experience, which was a burst rate of about 5 gigabits per second with 98 and 99% coverage. And we went ahead and verified this. But then we said, okay, is this overkill? Do we really need that many? Maybe we can do away with less. And in fact, we did. We took some of the Wi-Fi access points that were mainly there for capacity, because we really didn't need that much capacity on that floor. And with mmWave, we actually needed fewer sites. Next area we tested was, what would it look like if you had mmWave on a factory floor? You know, mmWave and metal, you know, people are very concerned. Of course, it doesn't go through metal. It doesn't go through some of these structures. It's very difficult to get the coverage. So we said, okay, well, let's test it. Let's put it on a factory environment and see exactly what we need to do, or how will we deploy this. And we were actually very surprised as well. The metal in this case actually helped because of all the reflections that we were getting across all the machines and the amount of metal that was on that factory floor. So we were getting a tremendous amount of reflections. So we were able to cover actually this factory floor with just 3 sites that were strategically positioned in the building, and 2.5 meters above the ground, fairly standard antennas, and with just 3 sites we had pretty much 100% coverage. Of course, if you had an IoT device that was inside the metal cage, you would not get that. But if you had any surface area, basically you would have coverage. So whether if you happen to be blocked by one in one beam, you would actually get a reflection from another beam. The other case that we've looked at, and again, these are all cases that we're trying to think, okay, the overall way to think about mmWave is, where do you need this capacity? And at the end of the day is where you have people or you have machines that need to consume this traffic. Typical area would be a train station, a transportation hub. Could be an airport, could be anywhere where you have you could have thousands of people at the same time, and they all want to have a good experience. And so it was this was a subway station in one of the Asian countries, very heavily used station. We actually figured out, okay, how does mmWave perform inside a subway station? So we did the same thing. This subway station was covered by Wi-Fi access points. We said, okay, well, let's reuse them and see how we do, since this Wi-Fi points already have power and things will be an easy deployment. And we did. There were a few little areas that have to be touched, but overall, we have been getting a very consistent result in which you can continue to have pretty much good coverage in all these cases. The other one, of course, it was a subway station. We did this airport in Europe, very similar. Why are we doing all this? We want to make sure that that this is applying, this applies well to all these cases. And this one was as well, very consistent. After we do this, many times, then you get comfortable that, like, okay, this is going to perform well. And so all the previous topics were based on coverage and prediction coverage, and then we go and measure where is the edge of that coverage, and we verify it on the field. And we made certain assumptions. For the last Mobile World Congress in Barcelona, what we did is we actually went a step farther and we did a simulation with actual devices. Sorry, not actual devices, but we actually simulated devices randomly placed across the whole floor. So what we did is we dropped in about 1,600 simulated devices, and we assume about 16 sites. And we actually have a tool that simulates the network and schedules every one of these devices based on a certain traffic model. Whether you're doing web browsing, where you're doing, you're posting a picture to Facebook. So we have a certain standard traffic model that we give to each one of these 1,600 devices. We go ahead and drop it on the randomly across the hall. And then we actually run the scheduler and figure out, okay, where, depending on where the device was, what would have been the throughput and the experience of that device. And you can actually check every one of these 1,600 devices and check what would have been the experience. And this was a live demonstration that we had at Mobile World Congress. So this picture is just an example of, we picked one user, for example, and he was doing web browsing. The experience it was getting, it was 4.5 megabits, 4.5 gig. So on a burst rate with very short latency. We picked another user that was doing an upload, and it was getting about 2 gigabits per second. So you could play with this tool on and pick different users and figure out what would be the user experience, assuming this network of 16 cell sites. And we had, I think with 16 sites, we had almost 100%, actually 100% coverage. And not only that, but in this one, I think we actually had both LTE and millimeter wave. So we were actually looking at the overall network throughput. So it's a very comprehensive simulation that we have. Okay, I think with that, that kind of wraps up some of the different ideas. And one thing before I conclude is to tell you that not only on the device, Qualcomm is coming up with products, but also on the infrastructure side. So as I mentioned, all these sites, you of course need a base station modem, and we do have a base station modem. It's the FSM 100XX, and that is going to begin sampling sometime this year. So we're excited about being able to participate with products as well on the enterprise side as well, on the network side. So with that, and before we get to questions, hopefully what I presented was useful to get people an idea of what the kind of things you would be able to do with millimeter wave, the kind of things we're experimenting with, the results we're getting. And I think in general, we see over and over that there is no end to where the amount of data need is going. We see it in basically any statistic that we look at. So when we look 4 or 5 years from now, the multiples, 4G, the amount of capacity that 4G has is just not possible to do it with. So how are you going to do this? You're going to need 5G. You're going to need solutions like millimeter wave to absorb that capacity. And what is the easiest way to deploy it? Well, maybe you can co-locate it with Wi-Fi access points. You could deploy, a greenfield network. You can put it on top of buildings. So lots of possibilities to try to absorb that demand. And in terms of where products are, well, we have it today. We have a saying here that we say 5G is here. So 5G is really here with commercial products. So luckily, we get to see this now, so very, very, very soon, and hopefully across in the rest of the world as well. So with that, I would like to maybe take a few questions, if it makes sense.
Yeah, thanks so much for the presentation, Alex. And to our audience, we've got a ton of questions here. Given the time remaining, we're not going to be able to get to them, but we have them cataloged, and we'll pass them on to Alex for potential follow-up. But to get it started, Alex, one of our audience members wants to know, besides fiber drops, what other backhaul options do you envision for millimeter wave sites in order to reach gigabit class speeds? Do you see millimeter wave serving as a backhaul mechanism in and of itself?
Yes, a very good question. And in fact, release 17 has this thing called integrated access and backhaul. Because yeah, if you locate the beams correctly, you could use it for both. You know, the spectrum is there, and the good thing with millimeter wave is very narrow. So you can actually say, okay, I'm going to have a different type of antenna or a different capability for my access side, and then on the back end, you may put another antenna or another beam or some other sector that doesn't interfere with the other one, that says, okay, this is going to be my backhaul. So you can have integrated access and backhaul, both using the same capacity. So that's a little bit the beauty, because there is not a lot of interference if you do things properly, so that you can do that. So that is a very good application. Yeah, you could have integrated access and backhaul, or you can go regular backhaul, as long as your backhaul is able to support, of course, the amount of capacity that the access side has, right? So yeah, you can do that.
Alex, we've got another question here. You discussed briefly millimeter wave propagation in an industrial environment and talked a little bit about the reflective characteristics. The question is asking if you can go into a little more detail on how interference was analyzed. And I'm also curious, you know, if you consider a mission critical robot, for instance, that's mobile in a factory floor, how do you ensure the reliability using millimeter wave? Is there something you can do around multi-point coordination?
Mm-hmm, exactly. Yeah. So yeah. So in the first part of the question, you know, you actually benefit from the reflections. So I mean, if you're talking about interference with the actual machines, we haven't really seen that, but interference from other, you know, in itself within the network, again, because of the low beams, if you can think of, you know, a laser pointer, I would say, reflecting everywhere, you're able to latch on to that beam, and you're able to change to another one if you have any kind of blocking. In terms of reliability, absolutely. The smart folks in the standards have been doing a lot of work around how do you increase the reliability for things that are time sensitive, time critical, like you mentioned. If you have to stop a machine, you have to stop it, you know, within a very short amount of time, in order of milliseconds. How do you ensure that that stop button is activated remotely? So the way you do that is by replication. So you actually coordinate multiple sites to actually send the same information, so you can make sure, you know, you do more and more assurance that that order, that message is going to get sent. So you basically, it's exactly what you're saying. You actually do a repetition of that same signal across multiple points, so that that reception is received.
We've got a question here about what we're actually seeing in the field, Alex. I know some of your colleagues have been out to test the various 5G deployments in the U.S., but the question is, there's anecdotal evidence of a high rate of signal drop as a user moves from outdoors to indoors. Is there any resolution to that beyond deploying a separate system indoors? And I guess to ask a more general question, with millimeter wave frequencies, is the indoor out coverage model, or I'm sorry, an outdoor in coverage model viable, or is that just a non-starter?
Yeah, it's very difficult. I will give you an example. Very difficult to predict. So I would say it's not possible, just because in some cases it works, it doesn't. In other cases, it doesn't work. And when things sometimes work, sometimes doesn't, then in my book is it doesn't work. So I'll give you an example. We have a courtyard here in our campus in headquarters, and we have two buildings on both sides of the courtyard. And when we put a millimeter wave site outside on the courtyard, it penetrates perfectly in one of the buildings. It doesn't penetrate at all in the other building, just because of the construction of the windows and the film that they put for the solar film that was put in on those windows. So there's a significant amount of variability between different types of construction, different types of windows, different type of glass, different concrete, wood structure. So very, very difficult to predict. So yeah, unfortunately, with millimeter wave, you can get lucky and get some kind of penetration indoors. But the reality is you have to do out to out and in to in, and that will be the deployment model. However, with careful planning, you can have contiguous coverage from out to in. You just have to, be careful. And of course, you always rely. You may not need, millimeter wave contiguous, 100%. You can always rely either on lower bands to carry you through these interruptions, so that you can have significant throughput when you're outside. You may have a potentially very small interruption. Maybe you go to a lower band 5G, and then you pick up 5G again when you're indoors.
Right. Now we've got a question around the example you gave of the analysis inside the Qualcomm building. Was that simulation run considering a wide open empty space, or a space configured like a traditional office environment?
Yeah, so that one was actually actual tests. So that one was not a simulation. So yeah, we actually went through these these walls and some of the glass that we have inside. So that we actually we put in signal generators where the Wi-Fi access points would have been, and then somebody with a scanner went around the building and verified those points, and then we did a prediction. So we did both prediction and actual verification. Yeah, and that actually goes for all the examples that I gave. We do the predictions, and then we go with a scanner and we take some sample points and say, okay, did this penetrate the particular wall? Of course, there might be, in this building, basically we follow the Wi-Fi deployment. So that was, in our particular case, it worked as we expected. There is, of course, if you have concrete walls between partitions, then that will not work. But it's unlikely, high-rise buildings and enterprises will have a significant concrete in between offices.
Alex, we've got a question about the discussion you led around the Las Vegas Convention Center. So in practice, would you envision that as 4 millimeter wave deployments for each operator covering the spectrum they've licensed? Is there any interference concerns in that scenario, or is it a different type of deployment model for a large venue like that?
Yeah, so every operator will have its own spectrum. So what we did is assume the customer experience of one operator. So every operator has their own spectrum. In the case of the United States, for example, AT&T has 39 gigahertz. Verizon has, I believe, both 28 and 39, depending on the market. So this could have applied to either one of them. So yeah, every operator has their spectrum. Every operator needs to make sure that the user experience is for their customers. So this was using, and typically I think a lot of them have about 800 megahertz of spectrum. So this was assuming one operator having 800 megahertz of spectrum. Another operator would have to actually use their 800 megahertz of spectrum to actually provide that. Now, the question that might be out there is, can you use the same box, for example, the same equipment to provide for both operators? I believe people are looking at that. Can we do that all with just one box and all the operators use it? It is possible. It's just there's a lot of business deals that have to happen for multiple operators to reuse equipment. So it's more of a business discussion than a technology discussion. But it is possible to have one box. Worst case, you have to put a box per operator.
And then Alex, one of our audience members would like you to address the case for millimeter wave in commercial laptops, given that most office buildings already have Wi-Fi coverage. Would it be just a matter of reducing congestion or something different?
Yeah, exactly. I mean, Wi-Fi, we love Wi-Fi. Qualcomm is, one of the largest providers of Wi-Fi chips in the world. So Wi-Fi has a lot of benefits, a lot of advantages. But the thing is, the demand is so large that you want to use as much spectrum as you have, whether that is Wi-Fi, whether there is 5G, whatever way, because what we see in the amount of requirements that enterprise want to put on laptops in terms of accessibility, speeds, have memory on the cloud, there's a lot of factors where you'll take what you can get. And if you have Wi-Fi and 5G, maybe you do both. So this is in addition. So we do see that as time goes by, you will need more than Wi-Fi on the laptops, especially for enterprises that want to run a lot of their applications on the cloud, and they require good response times. They require very high reliability, and even applications we don't even have today that we may come into the future. Also, security is another factor for enterprises. If you think about it, the millimeter wave signal does not propagate too far. So somebody from the outside of the building may not even be able to get any kind of signal. So you're almost providing a physical isolation from people on the outside to the inside from a security point of view.
I think we've got time for one more question. So, Alex, you gave the example of an enterprise campus. You gave an example of an industrial facility. Both of those environments kind of lend themselves to private networks. So if maybe we set the kind of regulatory piece aside, I know that 3GPP is currently looking at 5 gigahertz and 6 gigahertz for unlicensed NR. Do you see a scenario where that interest gets extended into unlicensed millimeter wave frequencies? Is there an opportunity there?
Yes, potentially. It's kind of related to the previous question. What spectrum is out there? What can you use today? What is the demand? There is, for example, bands in the 60 gigahertz that have been designated for 802.11ad, and the question is, could you run 5G millimeter wave on those bands under something that's called 5G NRU? It's 5G in unlicensed, And of course, all these things are possible. You can run licensed with the operator. You can run unlicensed. Like you said, it's mostly a business decision. And once the opportunity is there, of course, the standards are working on it. But definitely, there is a possibility for 5G NR-U on the millimeter wave bands around 60 gig.
All right. Well, Alex, thank you so much for the presentation and for answering questions today. I'd like to thank everybody for joining our session. We'll distribute some materials to you later in the day. Thank you for your time.
Thank you, Sean. Thank you for attending. Thank you very much.